Okay, here I've got a metal strap with a couple of magnets attached to the top. And I can hold this here and release it. Let me get back a little further, maybe you can see the whole motion. And when I do, it, of course, falls and attains some velocity at this lower point. Now, the mass of the two magnets is quite a bit bigger than the mass of the strap, but not so much bigger that the kinetic energy that the strap gains is completely negligible, but we're going to pretend it is. And we're going to ask if the mass of these magnets was much, much greater than the mass of this strap, then how fast would the magnets be moving at the bottom, assuming that there's no friction and no significant air resistance, no loss of, no dissipation of energy. So we model this. Now the actual strap is 30 centimeters long, but I say, okay, suppose we have a 40 centimeter strap. And I actually phrase this problem as a 40 centimeter rod with 200 grams up here and the rod mass being negligible. So we ask how much work is done on this object between here and here by the net force. Okay, well, and we know then that the work done by the net force is equal to the change in the kinetic energy of the system. And since the rod has no mass, presumably, or negligible mass, all or very nearly all of the kinetic energy will be in the 200 gram mass at the end of the rod. So we'll be able to set 1/2 mv squared equal to that kinetic energy and find the velocity. Well, how do we do that now? Well, we're going to do it with vectors. Okay, we have our displacement vector. We start here, we end here, so this is displacement. Now it doesn't matter that we're going around an arc. We're starting here, we're ending here. Gravity's going to do work depending on the displacement. Well, the force of gravity, of course, is down. And I'll note that you have to draw this vector of this length, and it's going to be 80 centimeters, 40 centimeters from here to here, and 40 from here to here. When you draw your gravitational force, you can draw it of any length because the units of the gravitational force are different than the units of your displacement. They don't relate to one another. So you can say, okay, the scale that I want for the gravitational force makes the vector this long. If somebody else wants a different scale, well, they can make it any length they want. Okay, I chose to draw them like this for no particular reason. Now, we know that to get the work done by a gravitational force through, or any force through a displacement, well, we have to project the gravitational force on the displacement, or the displacement onto the gravitational force, and then we multiply the projection by the vector we projected on, and we get the work. Okay, and the projection of the gravity on our displacement is, we can call the component of gravity parallel to our displacement. And in doing so, in this case, because this picture doesn't represent this case, in this case, both of these vectors are in the same direction, so that the projection of this vector onto this one, or this one onto this one, is just this vector itself, okay? So we can say that the parallel component of the gravity, of the gravitational force, is just equal to the gravitational force. So the work done by the net force is the gravitational force, the parallel component of the gravitational force times delta x. That is the component of the gravitational force in the direction of motion, but that is just the gravitational force times delta s. Now, F grav and delta s are both in the same direction, so that this work is positive. If they were in opposite directions, then one would have a positive sign, one would have a negative sign, and the work would be negative, wouldn't it? So you want to make note of that. That's very important. If the vectors are in opposite direction, then the product of the parallel component and the displacement would be negative. Okay, so in this case, the work done by the net force is what? Well, 200 grams has a gravitational force, experiences a gravitational force of 2 newtons, or 0.2 kilograms times 10 meters per second squared, again using the 10 meter per second squared approximation for the acceleration of gravity. So we have 2 newtons times 8/10 of a meter, which gives us 1.6 joules of energy. 1.6 newtons times meters, and a joule is a newton times a meter. So our change in kinetic energy is the work done by the net force, which is equal to 1.6 joules. If this thing is released from rest, and of course we could always give it a head start and give it some velocity at this point other than 0, but if it's released from rest, then the change in the kinetic energy is just 1/2 mv squared, mvf squared, where vf is its final speed as it goes through this point. That's our final kinetic energy, isn't it? Minus our initial kinetic energy, but initially the thing was at rest, velocity was 0, so 1/2 mv squared is going to be 0. So change of kinetic energy is then 1/2 mvf squared minus 1/2 mv naught squared, if you like. V naught is 0, so 1/2 mv naught squared is 0. So the change in kinetic energy, if you start from rest, is just 1/2 m times the square of the final velocity. Okay, well, we can solve this for Vf. How do we know this? Well, the change in kinetic energy is 1.6 joules. So we set 1/2 mvf squared equal to 1.6 joules and solve for Vf. Now, I'm not going to do that for you. We've done that in previous problems, but that's all there is to it. Now, recall, just to be sure, the units. 1.6 joules is 1.6 newtons times meters, because work is force times displacement, parallel force times your displacement. And a newton is a unit of force, so it's a unit of mass times acceleration. So it's the unit is kilograms multiplied by meters per second squared. Now that's multiplied by meters because, of course, the joule is a newton times a meter. And when we work that out, we get 1.6 kilogram meter squared per second squared. Now you should have already done these calculations. If you haven't, do them soon. If you set 1/2 mv squared equal to this, mass is in kilograms, you're going to divide by the mass and you're going to multiply by 2, but the kilogram is going to get divided out. You're going to get v squared in meters squared per second squared. So when you take the square root of whatever you have, your unit will be the square root of meters squared per second squared, and just give you meters per second. Now hopefully I'm telling you something you already know, but if not, you'll see it shortly. Okay? So from this analysis we can easily determine the kinetic energy of the mass at the bottom in the no friction case, and the velocity by setting 1/2 mv squared equal to the work done by the net force.